ln of x minus x.
Yep. Plus c. All right, well, I hope you all had a good weekend. So we are going to do something that I don't want you all to get used to this, but we are going to talk about the exam that is on Wednesday. We're going to spend most of today practicing some problems, and normally that will not be the case. I mean, I'm just letting you know. We kind of have time. I don't know how it happened, but we do have a little bit of time right now before the test to discuss. I'm going to show you some of my old tests, and we're going to work through some of the problems on there, or just at least talk about like what you would do. But the test that's on Wednesday, just keep in mind that exam 1. Okay? I know I'm recording, but let me just make sure my audio is on. You will have the entire class period for the exam. When you're done, you can leave. That'll be the format of every exam we take. So exam 1 is 15% of your grade. And then exam 2, 3, and the final are all 25%. And then homework and quizzes, I'll put quizzes here. That's 10%, if I'm not mistaken. So that's what's on the syllabus. So this is important to know because, this first exam is important, but it's not like a complete deal breaker. If you don't do well on it, it's not going to destroy your grade. If you do very well on it, it's not enough to kind of take your foot off the gas pedal, So in most Cal 2 classes, and I get a lot of grief for this from my colleagues, most Cal 2 courses will have their first test after 6.4. Okay, we're going to have our first test, and the last thing on there is 6.1. So if we were to have gone to 6.4, we would be going at this for a few more, probably another 2 weeks before your first test. And then you would have all the techniques of integration on there, and that would be a much more challenging test. And that's why I get grief from other faculty members here. You're like, it's not fair. Your Cal 2 students have it easier. They can take they only have to worry about it up to 6.1. Well, whatever. We have academic freedom, I guess. So I like to do it this way. That's why exam 1's worth a little less, okay, because you're not being tested on as much material. So I think it's critically important that you do well on this exam. Because exams 2 and the final are tough exams, all right? I think exam 3, historically, students do better on that because it's applications and there's a lot of formulas. And so as long as you can apply those formulas, it's very visual, so students kind of get that. Where the techniques, as we'll see today as we go through some problems, it continues to still be a problem like, what do you do, right? That always, when you're looking at an integral, it's like, okay, what do I do with this? Do I do U sub? Do I do integration by parts? What do I do, right? So later on it will be a little bit, exam 3 will be a little more like, I know what I have to do. He's asking for a volume, I have to do this, all right? Okay. So, you all ready to look at some problems? Are there any questions over anything before I start? Please, not all at one time. Raise your hand if you have something to say. Huh? Y'all are good? All right. Okay, so I was looking back at some old exams. So I'm going to show you 2 exams. One of these I gave spring 2016, the other one I gave spring 2015. And it kind of turns out that the 16 exam was easier than the 15. So I'm going to start with the 2016 exam. And I'm not going to show you everything. The first few problems had to do with the stuff on like arc sine and derivatives of those things. And I think that's still like Cal 1-ish type stuff. There's some product rule in there. Here's a hyperbolic identity that you're supposed to verify. Now, I am in no way saying that on your test you're going to have to verify a hyperbolic identity. But this just gives you kind of a flavor of what I have asked in the past. okay? So I asked, students to verify this identity. So they had to, write down what's the definition of cosine hyperbolic in terms of E, and then write down sine hyperbolic in terms of E, and then subtract them, and at the end they had to show that it turns out to be e to the negative x, all right? And those formulas for these, you have these, right? They're on your formula sheets. And then, let's see, more derivatives with some product rule. And then we get to the integration. So I thought what we would do is just kind of like talk through this, and let's just see how comfortable you are looking at an integral like this and knowing what you need to do here. And let's just also keep in mind that really we only have 4 things that we know how to do. Like, it's either something when we look at it, we recognize it from Cal 1. It's x to a power, in which we use a power rule, or it's U substitution, or it's integration by parts. I mean, that's really the only 4 things we have, right? So for this, what are you thinking? Yes?
Technically, you have all those things being added in the top and the
Yep.
numerator. So you can split it all into fractions over x cubed.
Exactly. You have multiple terms in the numerator, single term in the denominator. Let's split this thing up, and then let's go about them one at a time, right? So that's what we do. I'm not going to do it, but that's what we do. Let's look at what type of integrals we'd have. Negative 4 x to the 4th over x cubed, right? One of the, or 3 of the x's would cancel. So this is really just going to turn out to be negative 4x. You can integrate that. Okay, 7x over x cubed, that's going to turn out to be like a 7 over x squared. So you'll bring the x squared up and write it, x to negative 2, and then do your power rule. Okay, this right here, negative 2 root x over x cubed, you'll have to mess with the exponents on that one. That's like x to the 1/2 over x cubed. You subtract, you'll get a fractional exponent, and it'll be negative, but you can still use power rule on that. And this one, x squared over x cubed, you're going to wind up with like 1 over x, right? And 1 over x you have to recognize as natural log. Right? So every single one of those terms you should be able to handle. All right? Okay, now, the next one. I heard U substitution. Why U substitution?
Well, I mean, you can't really do integration by parts. You don't have a u or a dv, like it's a fraction.
Okay.
Right, so
Wouldn't you just use it just because the 1 over x is trapped within some can't square?
Okay, so the 1 over x is trapped in here, so what now because of that? What?
So that's your reason to use you said.
Well, maybe. The main thing with U sub is, here's the thing about U sub. We know that with U sub, we're initially looking for something in its derivative, right? Now, but we also saw that sometimes U sub worked even though we didn't see something in its derivative, right? And those were like weird cases. But in this particular case, you need to be able to see that you do have something in its derivative there. So,
1 over x times 1 over x squared.
okay, so if you rewrite this, secant squared of 1 over x times 1 over x squared dx, then this right here is the derivative, kind of 1 over x. Because 1 over x is x to the negative 1. And if we take its derivative, we get negative x to the negative 2, which is negative 1 over x squared. That's the derivative of 1 over x, right? So you're off by a constant. So that U substitution would be the correct U substitution.
And you can
Okay.
pull the constant out.
And the constant, remember we set this up, we say u is equal to 1 over x, then du is equal to negative 1 over x squared, x squared dx. We multiply both sides by negative 1, and so we'll replace this entire thing right here with negative du, and then we'll pull the negative out. Yep. Okay? Does that seem pretty straightforward? Anybody recognize this problem? It's a homework problem. I gave a homework problem. On this test, I gave multiple homework problems on the test. And that way students couldn't come to me like, man, that test sucked, man. I was like, they're homework problems. You should be able to do a homework problem. Would you agree with that? Okay. All right, what about this one?
Are you going to be that nice to us?
No, I'm not saying I'll be that nice. We'll look at the other test that I gave, and it wasn't that it was much harder, it was just that the problems weren't homework problems. So, people freaked out. Okay, so you should look at this and just say, hey, look, the derivative of natural log of x is 1 over x, right? And you have it there. So again, if you were to split this up, 1 over x times 1 over the square root of natural log x, then, dx, then if we let this be the u, just natural log of x, the derivative of that is 1 over x dx. And we have it exactly. We're not even off by a constant, right? So if we were to do that, the new integral would look something like this. And then that's just u to a power. Bring it up, u to the negative 1/2. Use your power rule. You're there, right? Something that came up with a few students is that there's a property of logs that you have to be a little careful with. Like we have this property back in college algebra that says that if you have natural log of x to a power that you can pull the power out front. You remember that? And that was a very useful property, and we'll use that a lot later on this semester too. But you have to be careful here because this power right here is only acting on this x. That's when you can pull the power out. And the reason this came up was because if you look at square root of natural log of x, you could look at that as being natural log of x to the half, like that, right? You cannot pull the power out here because the half is acting on the entire natural log. Understand? Now, if you had, so that is the square root of natural log of x. But if you had natural log of square root of x, then that is natural log of x to the half. And then, yes, that is 1/2 natural log x. So this is valid. This cannot become that. Understand? Just be careful with that, all right? All right, you want to look at another one? So far, is everything okay? Y'all seem to be more in tune to this than my Tuesday, Thursday class was. They were doing all sorts of weird stuff with these things. All right, what this one? So this is the first one that's kind of weird.
Can you separate the x cubed on top of x times x squared?
Can you separate the x cubed as x times x squared?
Yeah.
I can do that.
And then do the u sub as 1 plus x squared.
And then do the u sub as this?
Yeah. And then
So you must be doing your homework because this is a homework problem. Yeah.
that's
That's good, okay? Because if you haven't done that, if you haven't actually seen how you can make that x cubed split up, and this is your first time really trying to do this, then you're going to first probably try a u sub, and maybe you're going to go like x cubed, thinking that the derivative of that is 3x squared dx, and be all happy because you have x squared and you have x squared. But the problem is that's trapped. It's inside a root underneath on the bottom right in the denominator. It's a mess, right? So that's not going to work. But we can rewrite this as x times x squared over root 1 plus x squared dx. And then we can make a substitution that may not seem as natural, but 1 plus x squared works. The derivative of this is 2x dx. And you see that x dx right there? We have it right here. That x with that dx, those two together, right? X dx is this. We're off by a constant, so just half it, half this side, half this side. And I did this in the homework, right? So this one, yeah, we would be able to replace 1 plus x squared. So we're happy about that. We're able to replace the x dx. The only thing we have to worry about is that, and what do you have to do for that? Take this equation and solve it for x squared. So that becomes u minus 1. So if we take this, u minus 1 is x squared, then we have an expression for this, right? This will become u minus 1. And everything turns out nice at this point. I'll go ahead and rewrite it, even though I know this is in the homework somewhere. This will become, let's see, the x dx And the back becomes, what is it, half du? So put the half outside, half du. And then the x squared becomes u minus 1, that's on top. And then the bottom becomes root of u. And then what would you do with this? Maybe, that's working too hard though. You could separate them. You have two terms on the top, one term on the bottom, you split it into two new terms, and then you could do them each individually. So if you were to split it now, you would have, let's see, u over root u is root u. And then minus, and then 1 over root u is, why don't I just write that as u to the negative 1/2? And then this one is actually u to the positive half. We don't need that root anymore. And then you can just do power rule on each one. And at the very end, after you're done, plug u back in. This is u. We're there. Is this okay? All right. So that was a u substitution that wasn't as obvious, but if you've done your homework and you know that this is like an attack that you can make, then it's not so bad, in my opinion. This one. I don't believe this is in the homework, but it was definitely something we did in class. Yeah, so this was one of those ones where you're going to make a substitution that does not seem like it's going to get you anywhere, but it winds up getting you somewhere. And the issue here was that you can't move this x inside right now, right? Because you have the 10th power on a binomial. You have to expand that before you could pass the x through. So if we make the substitution u equals 4 minus x, the derivative of this is negative dx, which, we have dx there. We don't have a negative, do we? Right? So minus here, plus here. So now we have that. We have this 4 minus x, so we can replace this to the 10th power. And all we have to do is figure out what x is. So we take that and we solve for x, and we get x is 4 minus u. Just moving things around there. So we have something to replace everything we see, right? And then when we rewrite it, this new integral, the x is 4 minus u, put that in parentheses, and then the 4 minus x is u to the 10th, and then dx is negative du. So I put a negative out here and a du here. And that we actually like, right? That one we can do, because now you can pass this through because there's no power on that binomial anymore. The power is on that single factor. So let's see. Are you okay with this? So I just brought that negative back in, and I changed the order of things to make it plus then minus. Power rule, right? And you're there. I think what this first test always comes down to is how long is it going to take you to figure out what you need to do, right? If you can figure that out quick, if you can recognize what needs to happen, then there should be no issues. If every problem takes you 15 minutes to figure out what's going on, then that's when you start to run into issues. It's like you know how to do the problem once you've got the correct substitution, but that's part of the test, is to see if you can come up with that. All right, what about this?
What would have happened if you had reassigned variables on that problem so that you did a ultraviolet blue, you did integration by parts?
Okay, so let's see what would happen if you attack this with integration by parts.
Where you got it to the U10,
Oh, the one that already looked like do the substitution,
yeah,
and then from here do integration by parts?
that it made it easier?
I don't think so. No, because it's not going to be harder either. It's just your answer is going to be really ugly looking, and if you were to put everything back together, it would simplify out to the easier answer. Okay. So I think that would just be more work than you would want to do.
Parts from the beginning?
Now, from the beginning integration by parts, I think you might see the issue. I mean, it may still work. If I did integration by parts here, I have to choose a U and a dv, right? So what would you choose for U? You want to do this whole thing? Or do you want to use the x? See, this is where it would be up to you. So since you brought it up, what would you use for the U?
So I would probably do that thing we did with sine, where you pull out the fraction from what's inside, and then so I'd do 4 minus x for the dv, and then.
So you would do 4 minus x to the 10th here,
Yeah.
dx, and then here you'd use x.
Yes.
Okay, so du would be dx, right?
Yeah.
And v, you would have to integrate this.
So wouldn't it be like 1 negative 1 over 11 to the 4 minus x to the 11?
Exactly, yes, it would be. And then when you did your ultraviolet minus voodoo, right, it would be this times this minus the integral of this times this, right? And so you're going to have to integrate that one more time, which you can do, right? And you'll get an answer. And it would be correct. It just would look nothing like the answer the other way unless we algebraically turn them into one another. So integration by parts would work on this one. But I don't want to sit here and say, like, you can always use either one. It's going to work both ways. In this particular problem, it actually would work either way. But this still seems like a little more work than anything else to me. Okay? Let's see here. This one. If I'm not mistaken, this was also a homework problem. I was really, I guess, in a very giving mood this semester. Now, that doesn't mean they did well. I think I was trying to make a point when this is in the homework. But in the homework, it's natural log of y over square root of y. I just changed it to x.
Integration by parts.
So by parts, now why don't we see a basic U substitution? Is there a basic U substitution? Okay, if we did natural log of x, right, then the derivative of that would have to be 1 over x dx, right? And we don't really have a 1 over x, do we? We have a 1 over root x, right? So you can't just say, oh, I'll take the root of this side and root of this side. Because if you do that, I want you to be aware that if you take the root on this side, yes, you'll take the square root of 1, that'll be 1. You'll take the square root of x, that'll be root x, right? But you'll have root of dx also, and you don't have root of dx up there. And then you'll have root du, which is, we've never had our du being a root. So you see how that's problematic? So that doesn't seem like a very useful substitution because of this, right? We agree? Okay, so the only other thing maybe for us to go after would be integration by parts. So u here and dv here. So what would you choose for your u? X to the, so you want to use this 1 over root x? Right, this is natural log x times 1 over root x dx. And so this is really x to the negative 1/2. So if we put x to the negative 1/2 here, right, we can differentiate that. And we would get some new thing with x to a power, right? And then what would we put here? We'd only have one thing, right? ln x. Then we have to integrate ln x. And what are we going to get if we integrate ln x? X ln x minus x. We did that as a formula in class. So your new integral is going to have some crazy fractional exponent power of x here, and then an x natural log x minus x times this. That seems like a pretty nasty integral, doesn't it? So maybe we do something different in this table. ln of x here, because that'll give us 1 over x here, and then the 1 over root x here because that'll give us some weird fractional power of x here, right? And what you have across here is a power of x and a power of x. Do y'all see that? Do you see I've written nothing? I mean, this is part of what this is about. Can you see this thing happening before you actually make the decision? Now, sometimes you just have to write it down and just kind of go with it and see what happens, but I think it's a mark that you've really moved to a good place with this if you can start making these decisions about what's going to be what mentally before you actually commit yourself to something. All right, that fair? Like that? Okay, now this will be du is 1 over x dx, and then this one, v, 2x to the 1/2. When you integrate this, you add 1 to the power, right? So, and then you have a fraction out front that you have to deal with. So the new integral, right, this is going to turn into ultraviolet, so 2x to the 1/2, you could write that as square root of x, that's fine. Minus, leave a little space in case you need to pull out any constants. I can pull a positive 2 out. And then I'm doing 1 over x times x to the 1/2 dx. That's my new integral. It's that diagonal right here. And that, see what I'm saying? Like that's just going to be some power of x when I finish it up, when I clean it. Yeah, that's 1/2 minus 1. So this is really integral of x to the negative 1/2. And there's a 2 out here and minus and all that stuff out there. So that you could deal with, right? I'll just leave it. You could take that the rest of the way. Okay. Can I move on? Or cosine x, antiderivative. We know the derivative of this, all right? That's in our formula sheet. The derivative is, but not the antiderivative. So. Yeah, so integration by parts. You really only have one choice here because there's no substitution. Like you only have one expression there. I mean, you actually have two. You have this factor and that factor, right? But in terms of a substitution, like basic substitution, u equals something like the most you could do is use x, and then derivative's right there. But I already told you not to ever do that, right? Because all you do is rewrite the problem. So this one's going to be integration by parts. U dv. So u has to be arc cosine of x, and dv has to be dx. And then you need to know the derivative of that, which you do. It is negative 1 over square root of 1 minus x squared dx. So that's on your formula sheet, right? And then when we integrate this, you get x, right? So the diagonal doesn't look real nice right now, but let's see where this goes. X cosine inverse of x, that's your ultraviolet, minus a little space here. Can we pull any constants out of the diagonal, out of here and here? Maybe a negative? That's about it. So let's change that to a positive. And then we're going to have 1 over root 1 minus x squared, and then times this part, and then dx. Now this is a new integral, and this is just a basic u sub. If we use 1 minus x squared as our u, the derivative of that is negative 2x dx, and we have it almost, right? We're off by negative 2, so then we'd scale it. So the rest of this is just a basic u sub. You got that? Okay.
And you would use the 1 minus x squared
As the u for the u sub. Don't confuse it with the u here. It's a different, this is now a new integral. It lives in its own little world.
Yeah.
So yeah, you'd use over here u 1 minus x squared, and then du is negative 2x dx, and you want x dx, so you scale it by negative 2. It kills that off, right?
Yeah.
Yeah. And then when you're done with this integral,
Then you
replace that u with 1 minus x squared, and just slap it on the end of this.
Yeah.
Yeah. Yeah, so
Yeah,
don't
there
forget,
was
this is
one
still
last
part of
week.
your answer.
There was one like a few last week where it was like that.
Yep.
And like that one, I don't remember what it was for.
Mhm.
There was one you told us to do, and it was like over and over and over.
Mhm.
You had to slap it on each time. They were
Yep.
just getting longer and longer.
Yep. All right. Let's do something fun here. So let me see. We have technology. There's, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 21. There's 29 people on my roster. I don't know if everybody's here, but give me a random number between 1 and 29. Random number between 1 and 29.
3.
3. Okay, lucky 3. That's Andrew Bazan. Is Andrew here? Where's Andrew? All right. You get to tell us what to do on the next one. No one can help. Yep. All right, so nobody help. All right. Sorry, Andrew. I just want to kind of get a feel for what you're thinking.
Take the antiderivative. I guess it's a product, right?
That is a product.
So that separated. And,
Are you okay? So when you look at that, are you thinking more basic U substitution, or are you thinking integration by parts? Like if I had to like force you to make a decision on which one of those that one feels more like to you.
parts.
Okay. Now by parts, you know that you're going to create a new integral, right? And so one of those is going to be your v over in the original integral, and then in the new integral, it's going to be the derivative of that, right? And then the other one that you choose is you're going to have to take the antiderivative of it. So if you go with parts, which one of those would you want to choose as your u? Like which one would you like to see its derivative of over here in the new one? Okay, so let me put this here. If this is cosine, right, then in the new integral, you're going to be dealing with its derivative, right? Sine, negative sine, whatever. And then that means the x squared had to be this one, right? Which means in the new integral, you're going to be dealing with, nope, it's antiderivative. So 1/3 x cubed. So would you like to have an x cubed with a sine? No. Okay, so what would you choose here for you then? X squared, because in the new integral, it's going to be 2x, right? And then here, this has to be your cosine, and then that means this has to be sine. So your new integral is going to have those, right? Which isn't a whole lot better because you still have x here, right? But what could you do then? Just do it again, right? A new integration by parts, where you choose this to be your u and that to be your dv, and on that step, it's going to kill off that 2x down to a constant, right?
Is that easier than U sub?
Oh, there's no u sub you could do here. If you try and use x squared as your u, the derivative of it is trapped in a cosine, so you can't do that. And there's really no other basic U sub that you could try.
That was the first thing I thought, and then I was like, yeah, if you do the x, it's just going to be inside the cosine.
Yeah.
Still, so we can't do anything.
Unfortunately, you can't have that. And the main reason is because, like, if that's u, then you would have, u is x squared, du is 2x dx, right?
1/2 du, right, because you divide by 2.
Yeah, you could do 1/2 here, oops, and this would be x dx, but see, you don't have x times dx. You have cosine of x, then dx, so yeah, just not gonna happen.
And you can't, and the reason it wouldn't work is because, like, that's the argument, that x is
That's
sine
right.
cosine. That's not like its own x. It's not
That's
like
right.
multiple
It's the argument of the function.
x. Yeah, so
Yep.
you can't mess with it.
And you can never, This is one of those things in calculus. I don't know if you ever saw this. In calculus, like if you have sine x over x, that you're not allowed to cancel that. Because if you do, it's a sin. It's stupid, but, right? This is a sin. You can't do that. That's because that x is trapped. It's in the argument of the sine function, so you can't mess with it.
Different if it was 2x instead of 2x.
Where? In here? Nope, it would still not work if that was 2x. Because it's still trapped inside the cosine. See, because this right here, right? Even if it was 2x, your du over here is 2x dx. You can replace 2x, right? That's what you would have to replace, that 2x, but what would you be replacing it with? This dx can't be there, because this dx is not part of this. You see that? Even though it looks like 2x dx, there's a huge separation here. You must do this before this, so you cannot just peel those off on their own.
If it was x cubed, you could do it.
If what was x cubed?
Cosine x.
If inside here was x cubed, then you would use the substitution u is x cubed, because the derivative of that would be out here off by a constant. Okay, thank you for letting me put you on the spot. That's I think that's helpful for everyone.
Trying to work down the exponent on most of these problems.
Am I trying to do what?
Like work down the exponent, like. You
On
would've-
this I would, yes. You just keep on chipping away at that x squared.
So is it, I mean, would it be like a bad rule of thumb to like, especially with trig identities, always do the u sub as something with an exponent?
Well, you want to make a rule of this?
Yeah, I mean, that would be, the question being asked is if you see a function here that's going to just keep on kind of swapping around, we call a function like this cyclic. Any function that when you take its derivative, it only goes through like a certain number of things. So like if you take derivatives of cosine, you get sine, then derivative of sine, you get cosine. So you know no matter what with this one, it's just going to be sines or cosines, right? If this one here is a power function, then you know with integration by parts, you can just chip away at that power, right? So yeah, if you're looking for kind of a rule of thumb, if you see a power of x here, and you see something that's going to cycle through, like e to the x would be the same way, right? E to the x here would just keep on being e to the x. Then yes, you want to do integration by parts, let this be your u, and just kind of break it
So
down.
what if instead of x squared it were e to the x?
Well, let's see. I think it's coming. So I did random generator here. Hold on. Okay, 25. Emret? Did I say that right? Emret? Okay. Oh, there you go. Look at that. Look at that. You called it. You called it. Okay, so Emret, do you have an idea?
Yeah, exactly like you said.
What? But what, okay, so integration by parts, okay? But do you know already what's going to happen with this? Because in the last problem, it was like x squared, and we knew that we could do it twice and get the x squared to go away. Do you know what's going to happen with this one?
It just kind of goes away on its own.
Does it go away? Like if you let this be your u,
It'll be the same.
then when you take its derivative, it's the same thing, right? If you let this be your dv, when you integrate it, you're going to get sine. So in the new integral, I'm not even going to put u in du anymore, okay? Can I just do this just for speed? That's your table, right? Your new integral is going to contain this, which is not any better, right?
It's just going to keep doing it over and over.
And if you did integration by parts again, you're going to have the same situation happen. But this is the one where it appears on the other side. You get the integral you're looking for to appear over there, and then you subtract or add it to both sides, and then divide through by a number. So we did a problem, well, I think we did e to the 2x. And so this was the one, it was, in the notes, it was the rabbit out of the hat problem. This is the one, all right? So is it easy to recognize that now that we've talked about like this one compared to the previous one? Is it easy to recognize that this is going to be rabbit out of hat? Yes? Yeah. Okay. Good. All right. So who's next? Let's see. I'm not going to work through that one. 14. So there's 10. Eric? Where's Eric? Huddleston. Is that you?
Yeah.
Okay. Sorry, I don't know all your names. I'm never going to learn them. But I've met with you. I've met with y'all, so I'm starting to learn a little bit more about your life, which I can remember those sorts of things better. All right, Eric, you're up. Due to the random number generator through Google.
Let's see.
Let's let Eric think through this because Eric is somehow emulating everybody in the class right now. All right,
I'm pretty sure it'd have to be integration by parts.
Okay.
Because I mean, if you did U sub, I mean, how would you the e to the x cubed?
Mm-hmm.
You get this. Well, you get e to the x cubed, and then you'd have to do the x cubed,
Mm-hmm.
right? Then you get 3x squared on the outside,
Mm-hmm.
and I don't really see that.
Okay.
And then
So, I don't want to force your hand here. You're saying you're thinking. That's what you're doing. Okay.
go ahead.
No, I want you to steer the ship here. That's all.
Okay. I was just saying. Well, I mean, that would be good. Like if you could do u sub with the e to the x cubed, because you'd get 3x squared times e x cubed, right?
Mm-hmm.
If you take the derivative. But then what about the 3x squared?
Yeah.
Is that in? That's not really in. Well, I mean,
I'll give you a slight hint here. You're saying right now you're entertaining. Originally, you were entertaining integration by parts,
yeah.
and then you kind of backed up and said, "Wait a minute, maybe I can do a u sub."
Yeah.
And the u sub that you're thinking is maybe the e to the x cubed,
Yeah.
because the derivative of x cubed is going to give you 3x squared, and somehow maybe you can get that.
Yeah.
Okay, so if you did e to the x cubed, let's just go with that just to see what would happen. The derivative of this would be,
3x squared.
well, e to the x cubed times 3x squared. That's a little problematic because that's u, right? So that's u. You can't mess with that anymore.
Yeah.
Now you're looking for its derivative, and that derivative
Isn't there?
isn't there. So I still think that you should entertain this idea, but I think e to the x cubed was too much.
Yeah.
So what could you do instead of e to the x cubed?
Or just the, you could do just the x cubed.
Just the x cubed. Let's try that.
Because
Well-
at least you could do it with, I mean, the 3x to the fifth, right?
Okay, let's entertain this, all right? Yes? Now, before I do this, I want to show you why integration by parts is not going to be something worth going after right off the bat. Watch. If I do integration by parts, I would hope that your instinct would tell you to go with this is your u, because you can chip the powers down on that, right? Yes? Yes? What? Oh yeah, you could pull the 3 out. Yeah, you could pull the 3 out. I'm going to just keep it with me, because I like to mess with the numbers, whatever. Okay, so that's what I would have, right? If I let the u be the 3x to the fifth, and then took the derivative, I'd get that. But then here, dv would have to be what? E to the x cubed dx, right? And here's where you have a problem. Going up. Because the antiderivative of e to the x cubed is not e to the x cubed. The antiderivative of e to the x is e to the x, but e to the x cubed, it's not this, right? I mean, think about this. Is the derivative of this? No, because you have chain rule, right? So that integration from here to here is not something obvious or within our grasp. Understand?
Yeah.
So even the integration by parts off the bat is going to be problematic. This substitution might work.
Yeah.
Let's see. If we were to stick with this substitution, then I can rewrite x cubed, that x cubed right there, right, with u. So that's going to be e to the u. I need to see somewhere in there a 3x squared dx. I see a 3, I don't see x squared. Unless I rewrite it as x squared times x cubed, e to the x cubed, right? If I rewrite x to the 5th as x squared times x to the 3rd, then it works. So 3x squared dx, 3x squared dx, I've got this taken care of, right? The only thing I don't have taken care of is what? X cubed. But x cubed is u, right? So it works. It works. Look, this is going to become 3x squared dx becomes what? du. All right. And then x cubed becomes u. And then e to the x cubed becomes e to the u. Okay, now here. Let's hold on. Don't say anything. Everyone be quiet. Oh. Jeremy? Where's Jeremy? Oh, you're up now. This is its own problem now, right? This is its own problem. So just clear the slate, and if you were looking at that, and if it helps, if you were looking at this, if you replace them with x's, if that helps. So what do you think there, Jeremy? Any ideas?
Well, I mean, it's easy if we stick with the u. You can't use the integration by parts because u of u wouldn't make any sense.
Okay.
So now since you put it as x, maybe we can use integration by
You could, yes, exactly. We can do integration by parts again. Now, the problem with the integration by parts formula is that we use u and v.
Yeah.
But if you've already made a substitution earlier and you're calling something u, you can't use that u and v anymore. But you can still do integration by parts.
You can use it like
W or something like that. So let's go with that. Now, the reason why you're doing that, you see that one of these you take the derivative of, and the other one you integrate, right? And that's going to be nice. Okay, good. I think Jeremy got us there. Not u, W is going to be u, right? And dv, we can still use that, is going to be everything else, e to the u du. So this was a problem where you had to do a basic U substitution first, and then after that, we have to do integration by parts. So dw is du, and v is, thankfully for us, e to the u. So this integral becomes this times this, u e to the u, minus, and we don't have any constants, so integral e to the u du. And that is a pretty straightforward antiderivative, right? So we get u e to the u minus e to the u plus c. And then u is, don't forget, x cubed. So that's it right there. Yeah. Now, if we wanted to check our answer, we could factor out an e to the x cubed and then do product rule. Yes?
Would you say that a lot of the times if you see an e to a variable with a power that you would, and if you're also going to do integration by parts, that you would want to have the variable with the power as the u?
Would I say that if I ever saw that, that's what I would do?
Like for the most part, most of the time?
I know what you're asking me. And this is probably one of the most common questions I get, from Cal 2 students when they're seeing this stuff. I think what you're looking for is kind of a template as far as like what to do that's going to help you recognize things. And my answer to that is I guess no. Because here's why. Because if this was x to the 6th, it wouldn't work. Okay? If this was x to the 6th, then this substitution just would not work. And so I'm trying not to, look, anytime I can give you something in this class that is always going to work, I'm going to give you that, okay? But with these integrals, every one of them is so uniquely its own animal that I can't just hand you like a, if you see this, do this. If you see this, do this. Because it might catch up with you, it might bite you, I'm sorry. This is what makes it challenging. I kind of got into a little heated debate with my last class. I think I really upset one of my students because we were talking about something that they teach. A lot of the tutors might show this to you, and it's not wrong. But let me I don't even know exactly what it is. It's like LIATE, right? So you've seen this? Can you explain to us what it is?
It's just like a key kind of to look towards if you're going to do integration by parts, which one to look for to make it to be a U.
Okay,
So
yeah.
Log, inverse, algebraic, trig, and exponential.
Yeah, so this is a cute little thing that you can use if you're going to use integration by parts and you're trying to figure out what to make your U and what's your dv. This tells you that you should always use, for your U, right, for the U part, not for the dv, but for the U, you should always do a logarithm as your U first. Like you should do that. And if there's not a logarithm, then you should do an inverse. If you see an inverse trig function in there, let that be your U. And if there's not an inverse trig or a log, then anything algebraic, like x squared. Okay, and if that's not there, then if you see like a sine function, let that be your U. And if that's not there, you can use exponential. Okay? A lot of students do find this helpful. I don't teach it. Okay? And the reason I don't teach it is because from day one, I've been trying to get you to understand that integration by parts is a transferring of the derivative. That one function is going to get differentiated, the other one's going to get integrated. And the sooner you see what the new integral is going to look like here, just everything's going to run smoother. If you're relying on, and this is what I think what pissed off my student, because I think he uses this and he likes it and it's helped him, which if it helps you, great. But I was kind of making fun of it a little bit. I was like, this is very robotic. It's like, I'm looking for a log. I don't have a log. I go for an inverse function. There's not a lot of thinking here where if you're trying to see how things are going to change shape in the formula with the integration by parts, I think that's a much deeper level of thinking, personally. That's just, if you like it, go for it. But I'm not going to teach this. It's kind of like FOIL. To me, it's kind of like that thing FOIL that they teach in college algebra. We still say it to this day. We'll say, okay, you have to take like this means that you do this and then you do FOIL, right? FOIL. So it stood for first, outer, inner, last, and it's cute. It's very cute, but it's not yet. This does not help you understand what expanding polynomials is all about. Because if you have something that's more involved, right? And I ask you to expand that, FOIL's gone, right? You have to understand how you multiply polynomials. So that's why it's kind of the same with this. Like, yes, I could teach this and it would maybe give you a little bit of assistance, but you are missing the deeper picture here, all right? Opinion, yes, I'm entitled to it, yes?
Makes sense.
Okay.
Because like rather than teaching a formula, you're trying to teach the actual thinking behind that. Like,
It's what my professor told me, Dr. Richardson, which I had tremendous amount of respect for, and he was all about trying to create critical thinkers as opposed to just giving you some little cute thing that's going to let you get through the problem without actually understanding it. And his big thing was transferring the derivative. You're transferring the derivative. That's what you're doing with integration by parts. That's it. It all comes down to that. All right. Let's see. And there was a bonus problem on this test. So it was proving an induction formula. Now remember I did the induction formula for sine to the n? I did that, right, in class? It was a mess. I believe this might be a homework problem. Yes, this was a homework problem, and I do not believe that I did a video solution for any of the proofs. So in the video solutions for 6.1, I do not believe I did the inductions. That's a bonus problem. So if you were to have time for this on the test, you would have had to have created this formula, like shown where it came from. All right, so that was my spring 2016 exam. It was 10 questions, okay? If you came in late, I did mention something to the students at the beginning, and that is, today is kind of a unique day in the sense that we actually have time to talk about the exam, but from here on out, I would not anticipate that we will be able to spend an entire day reviewing like this, all right? All right, so look at this, spring 2015, here we go. First one looks very familiar, doesn't it? So that one, multiple terms in the numerator, single term in the denominator to split it up, right? Okay, no big deal. Okay, how about, I liked calling on people, that was fun. Let's keep doing it. Number 7, 10. Margie? Oh, wait, where's Margie? She's not here. This is a different. Eric, you got called again, but I'm not gonna do that. Okay, how about Lewis? All right, Lewis. What's up? What do you see here, Lewis? It's close to the identity. The identity would have to be 1 minus cosine squared, and then you could turn it into sine squared. I'll let you keep thinking, and let's let Lewis think about it, okay? Okay, that's enough time, Lewis. I'm kidding. So this, see, if you wanted to isolate sine, you would bring it over, and then you get 1 minus, so we can't. It's not exactly the identity. Would be nice, though, right? If this was sine squared, then you take square root, it's just sine, then the sines cancel, it's just 2, and you're integrating 2, and it's just 2x plus c, and you're done. But that's not what it is.
Could we do 1 plus cosine squared to
So you're thinking U substitution here? Like this? So if you took the derivative of this, derivative of 1 would be 0, right? And the derivative of cosine squared x, you would have to use chain rule here. So you would first bring the 2 out, cosine x, then times the derivative of cosine, which would give you negative sine x, and then dx. Agreed? And I think that's an issue here, because you've got a lot of crap in this thing, don't you? And you've let this be u, which is great, but all you have up here is 2x sine x dx, right? That's all you've got. And you've got some cosines in here also. So maybe you could make this work, but if I were you, I would start thinking, maybe that substitution was a little bit too much. So if you had to do it again, would you try something different? So if you do just sine, the cosine is trapped though, right? So you can't do just sine, but you're close. Remember what cosine squared x really means, right? This denominator is really, this is square root, this is 1 plus, this is really cosine x squared, right? That's really what that is. So last time you picked the 1 plus the whole cosine squared x. Just cosine? If you pick just cosine, then you're going to have its derivative up there, right? So let's try that. Let's let u be just cosine x. Its derivative is negative sine x dx, which I have. What about that 2, though? That 2 is, I don't have a 2 here, and I don't have negatives, so what could I do? You could just pull the 2 out, or you could just multiply both sides of this by 2, right? Either way. I like to work with this. Even though I could pull the 2 out, I like to just work with this. So I'm going to make this look like 2 sine x dx. So I'm going to multiply both sides by negative 2. Yes? Question?
I was just asking, wouldn't it, for the u, wouldn't it be cosine 2x? Because you have the cosine 2x in the square. Cosine squared x means cosine x squared. So when I pick my u, I don't have to pick the squared. I can just pick the cosine. Well, I was just saying, cause wouldn't it be easier, cause then we would have the two sign